Okay, the last item that we're going to take a look at in this lecture has to deal with estimating the pressure drop across a tube bundle. Now, this is going to have significant implications to the performance of the heat exchanger unit or cross-flow heat exchanger or whatever it is that we're looking at that involves the tube bundle. What we're going to do, we're going to begin by looking at a video clip of an aerial cooling unit, which is a gas-to-gas heat exchanger. And so I'll begin the video clip. And so what you can see here is the aerial cooling unit. This is actually on the exit side where the gas is coming out of the tube bundle. But air is being forced, atmospheric air, up through a tube bundle at the top of this unit. There you can see one of the fans. In the upper right-hand corner, we have the infrared camera showing this is a case where we're cooling a gas. And so air is being forced up each of these different units. There's a big fan connected to an AC motor, and there you can see the AC motors. The airflow goes up through and across the tube bundle, which is then cooling a gas. And so that is a gas-to-gas heat exchanger, and sometimes also referred to as being an aerial cooling unit. Now, when you're looking at that clip, what you'll notice is that we had, first of all, the fans on the bottom with AC motors, and consequently there's a coupling between the pressure drop and the performance of the fan. And that's why it's quite important for us to be able to estimate the pressure drop across a tube bundle. And quite often the pressure drop is written as being delta P. So schematically looking at what we may have going on in this type of a scenario, I'm going to draw out the configuration that we just saw in that video clip. So here we have a tube bundle, and in this case the flow is going vertical up and through the bundle. Now it very well may be that there are fins on the tube bundle which could increase the pressure drop, but we won't worry about that right now. So let's say this is our tube bundle and it is confined within some sort of a duct, and we have forced convection heat transfer. And so below the tube bundle we have a fan unit that is forcing air to flow up and across the tube bundle. And consequently we're interested in being able to determine what the pressure drop is across this tube bundle, because that has important implications to the performance of the fan and also determining the volumetric flow rate that would be coming through this system. And that's why we want to be able to determine the delta P. So let's take a look at the fan curve. So typically when you're selecting a fan for an application, we'll have fan curves, and sometimes they'll have static pressure, sometimes they'll have inches of water, but then you use your OGH to determine what that is in pressure. And on the horizontal axis we'll have volumetric flow rate. It could be cubic feet per minute, standard cubic feet per minute, meters cubed per hour, something like that. And what you'll then find is you're going to get a series of curves that may look something like this. These are the different fan curves. And as we go out in this direction, this is increasing RPM. So that would be the rotations per minute of the fan. And typically in the video that we just saw, the fans were being driven by an AC motor. Now, depending upon where you are, it depends on the power grid. But if you have 60 hertz power, typically that gives us 3600, 3560 is sometimes what is used to allow for slippage. But 3560 RPM. So you wouldn't want these fans spinning at that high of a speed. Or rotational rate. So what you would do is you would either have a pulley system to reduce the rotational rate, or you would have a gearbox that would reduce the rotational rate. If you have 50 hertz power, other parts of the world have that, and there we would get 30 or 3,000 RPM would be what would be coming off of the motor, the electric motor in this case. So anyways, the increasing RPM is going in that direction, depends where you are, what it might be. And using belts or a gearbox, you can change the RPM that you're at. Now, the system itself, as determined by the pressure drop, so if we're looking at the pressure drop, this pressure drop, delta P, is going to be a function of the volumetric flow rate going through the system. And consequently, as we change the volumetric flow rate, we will have a curve that does something like this. And that would be what they sometimes call the resistance curve. And what would happen, dependent upon the RPM that you are operating at, the intersection of these two curves is where your system would be operating. And so it would depend upon RPM. Normally, you don't want to be operating right up there. You usually want to be operating a little bit lower because fans themselves have efficiency. And so you want to be operating a little bit lower than that intersection. But that is why we have an interest in being able to determine this. I am not going to give you the equation for determining that. It's kind of a long one, and it varies depending upon which textbook you're using. There are different correlations. But this gives you a background in terms of why it is that we may want to know what the pressure drop is, because then this would relate directly into the volumetric flow rate that our unit is operating at, and that would have direct implications into the convective heat transfer coefficient as well as the amount of heat transfer that we have going on with our tube bundle. And so anyways, that gives you a bit of a background of tube bundles and industrial application with an aerial cooling unit.